Good morning, welcome to Lionheart Academy. Today we're going on to our trigonometry lesson number 33. For the past few lessons we have been talking about the graphs of trig functions, sine, cosine, tangent, secant, cosecant, cotangent. Today we're going to start a new topic, the inverse trig functions. Okay, the inverse trig function. Now before we talk about inverse trig function, let's just go ahead and get started. Start with trig function. Like, what exactly is a trig function? Now when we talk about a trig function, or a function in general, usually we have a view of an input and output, a flow chart. Okay, so this is a basic form of a function. Now a trigonometry functions let's go ahead and talk about trigonometry functions in general. Has an input and it has an output. Okay, so what do we put into a trig function? Well, what do we put in? We actually put in, the input is usually called x, output is usually called y. Okay, so this is a trig function. Sine, cosine, tangent, doesn't matter. The input usually represents this, a measure of an angle. So the input usually for the trig function represents a measure of an angle. And what do we get out? The output usually represents a ratio of size, okay, a ratio of length that's related to the angle, right? So if you remember when we defined it in using either the right triangle or using the unit circle or using the circular definition, the input is usually measured of angle, the output is the ratio of length. Okay, the output is ratio of length. So as we can see, if I go ahead and draw a diagram very quickly, as you can see, when we say, okay, we rotate this rotation, right? We rotate the terminal side to a certain place, and then we call this a terminal point, and so this is the angle theta. So the sine, cosine, tangent, they are all segments. They're not just ratios, right? They're just because they're the opposite. Remember, they're the ratio of the opposite side. This is the opposite side over the adjacent, or the ratio of adjacent over the hypotenuse, or the ratio of over the hypotenuse over the opposite or over the adjacent. So it can be different situations. However, if the radius happen to be 1, then the answer can doesn't have to represent just a ratio of length. It can actually represent a segment of length. So the output can represent segments. Okay, it's not just ratio of length, but also represents segments. Let me put the one over here. Okay, segments related to the angle. Okay, so for example, this, if the r is 1, then this is sine of theta. This segment is sine of theta, and this segment is cosine of theta. Okay. Now, there's another aspect to what we're doing. This is there is a measurement of the arc. Okay. When we draw the unit circle from here to here, this is the arc, and then we usually represent the arc by call s, and s equal to r theta. Right. So when we do theta, when we do sine of theta or tangent of theta, we can represent this. If r is equal to 1, like in this case, if r is equal to 1, then s would be equal to theta. So that means the angle can also represent an arc length. Okay, so the measure of the angle can also represent an arc length. So the input theta can be considered either as an angle or as an arc length. So we say, okay, if we have this arc length in radian, this is 1 pi, and then what would the sine theta, what would this segment be related to this arc length? Okay, so that's a very useful information for mathematicians, for engineering, for people who construct, for architects in the past throughout history. Okay, so this is a relationship very important that will allow us to relate this arc length, not just this angle, but this arc length to the segments, to different various segments, like to the tangent segments, to the secant segment, to the cotangent segment, different kinds of segments that's related to this arc length based on the arc length. Okay, because this arc length theta is the same as the arc length s, is the same as theta when the radius is equal to 1. So arc length is also related. So as you can see, the input can be several things. It can be the measurement angle most commonly, but it can also be an arc length. And the output can be a ratio of length, like a sine over opposite over hypotenuse, or it can be just a segment that's related. I'm sorry, it's kind of hard to see. It's related to the angle. Okay, related to in segments, related. Let me go and try to write it a little bit more clearly. I'm sorry, related to the input angle or arc length, input theta. Okay, now this theta can be both arc length or angle representing both. Alright, so this is the basic input and output of the trig functions. So what about the inverse? What does the inverse function look like? Or what does the inverse function mean? Well, the inverse function, it basically means this, is when we have, when we switch the input and output of a function, then we have the inverse of such functions. Okay, so let's draw another flow chart here. So if we have the inverse of trig functions, then our input, okay, is still going to be called x, okay, and output is still going to be called y. Alright, so that means the original output will become the new input. So the input of a trig function will be a ratio of segments. Okay, segment length, or ratio of segments, or just segment length. Let me go ahead and write it down. Or it can just be a segment length. And then what do we get out of them? Well, we get back the measure of the angle. We get back the measure of the angle theta, but the measure of the angle theta can also mean the arc length. We can also get back the arc length that's related, arc length s, in which case is equal to r theta, and when r equal to 1 is exactly the same. But even if r doesn't equal to 1, we can still find out what the arc length is very easily. So the inverse function, inverse trig function, does two things. Okay, I'm sorry. Let me write it more clearly. The inverse function takes the output of the original trig functions and then give you back the original input. Okay, so it takes the segment length, the ratio of segment lengths or segment lengths, and then it will give you back the measure of the angle theta or the arc length. So that's why the inverse trig function is also called arc functions. Arc functions, as you can see, is arcsine, arccosine, so arc functions. Alright, because they return you the measurement of arc length. Alright, so we have 6 trig functions, and therefore we have 6 trig inverse functions. Okay, now so we have sine and we have inverse of sine. Now inverse sine, we can write it like this. Alright, so let me go ahead and make be a little bit more accurate here. So let's go ahead and say y equal to sine x. So if y is equal to sine x, that means x is equal to sine inverse of y. Okay, now this raised to a negative power sign represents inverse. So we don't say sine to the negative first power y, we say sine inverse of y. Another way to say this is we use arc, A-R-C-S-I-N, arcsine of y. So on your calculator, you probably will see more of the inverse sign. Sine of inverse, okay, sine to the negative first power, or a sine inverse. Actually, we should read the sine inverse. Most likely your calculator will have this above your sine, cosine, and tangent, but you also sometimes will see arcsine or A-sine on your calculator, the acronym A-R-C-S-I-N, arcsine. Okay, so I like to use arcsine because it's a little bit more clear to see what we're actually doing. We're not this is the inverse, not the reciprocal. Okay, because you remember an expression raised to negative first power is the reciprocal of the power, so you might get confused. Okay, but anyway, so this is the basic terminology here. Y equal to sine x, okay, would be equal to this. So on the other hand, if I say y equal to cosine x, okay, then that means cos x will be equal to cosine of inverse of y. Okay, and then, or another way to say this is called arc cosine. of y. Okay, but this is actually not. Actually, I should say this is not true in all cases. There are certain cases it's true, certain cases not true. Okay, the reason is x and sine and y. We have some issues that we have to talk about before we can qualify this as true all the time. Okay, so we'll come back talk about the conditions though. Well, because just because y equal to sine x, x doesn't not necessarily equal to inverse sine of y. Okay, there are certain cases it's not true. We have to talk about some qualifying issues here. Okay, all right. So let's talk about the qualifying issues. Okay, let's go ahead and look at the graph of sine first, and let's see what's going on. Alright, so this is a sine graph of sine x. Okay, let's take a look at graph of sine x. Now, sine function is a continuous function. Okay, any function for any graph or any relation of x and y to become a function, you have to pass the vertical line test. I'm not sure if you remember vertical line test, but vertical line test means if I draw a vertical line and then through any point of the function, it cannot pass the function more than one time. So as you can see, the sine function is okay. It passes vertical line test because this vertical line, any point, if I draw a vertical line, it is not going to pass the function more than one time. Now let me show you an example of something that does not pass the vertical line test. For example, if I do x equal to y squared. Okay, now this is not a function. This graph does not pass the vertical line test. As you can see, if I draw a vertical line here at pi over 2, it will pass at the top, and pass first time at the top and second time at the bottom here. So it passes more than one time. So this is not a function. So the vertical line test determines whether it's a function or not. Now sine, of course, it is a function. Okay, it passes vertical line test. However, it is not a one-to-one function. Now, what do I mean by one-to-one function? Now, one-to-one function has to pass a horizontal line test. So if I draw y equal to 0.4, okay, this is a horizontal line, and as you can see, this horizontal line passes through the function more than one time, right? It passes through the function more than one time. Okay, actually, let me use 0.5. Okay, let's use 0.5. Let's use 1/2. So as you can see, okay, y passes through 0.5 more than one time. Okay, what it means is that this sine function would give me outputs that are not unique to its input. Let me explain that. What do I mean by that? That means for different inputs, I can have the same output. So if I put in pi over 6, I can get 0.5 as my output. If I put in 5 pi over 6, I also get 0.5 for my output, right? So that means, and then it actually keeps going, so I can have more. It actually goes to 13 pi over 6 as well. So that means my input, okay, pi over 6, 5 pi over 6, 13 pi over 6, all give me 0.5 as input. Let me show you as a diagram here. So let's say we have this chart. Is my input x, okay, and through my sine of x, I get my output, right? I get my output y. So that means if I put in pi over 6, okay, I would get 0.5, right? But if I put in 5 pi over 6, okay, I will also get 0.5. Okay, so that's okay. And if I put, let me go ahead and put in one more number. The next number is 13 pi over 6, right? So if I put 13 pi over 6, I still get 0.5. Okay, so that means for all these three inputs and more, I get the same output. Okay, that is okay as a function. For a function, you can have multiple inputs giving you the same output. But remember, what we talk about is that when y equal to sine x, right, x has to be equal to the inverse of y. So when we do the inverse, remember we have to switch what? X and y back and forth, right? So if we do arcsine now, if we do inverse sine or arcsine, okay, if we do arcsine function, now there's a problem, because if I put in 0.5, right? If I put in 0.5 into arcsine, which original input do I get back to? Do I go back to pi over 6? Do I go back to 5 pi over 6? Or do I go back to 13 pi over 6? Or do I go back to all of them? Now, if I do all of them, Okay, I mean I could do all of them, then that would not be a function, because then now I have one input and I have multiple outputs. That's not a function. One input can only give me one output in a function. So where do I go? Where do I go, right? Where do I go? So this is a problem involving sine functions and cosine functions and tangent as well. When we do their inverse, there is a problem. Okay, we don't know, when we put in 0.5, we don't know which one to go back to, unless we do some restrictions in the terms of the domain. Okay, in terms of domain of this inverse function. And in terms of domain, actually we restrict the domain of the original function, so that when we when we do the inverse, we will know exactly what we're going to have. So let's take a look at this. Okay, I'm gonna turn this off just for now. Alright, now so what we have to do is, the mathematician decided that we are going to limit the domain of the piece of arc that we are going to use for sine from negative pi over 2 to positive pi over 2. Now why do we do that? It keeps going off on me. Okay, why do we have to do that? Because from negative pi over 2 to pi over 2, it went through the sine value goes through all the unique sine value from negative 1 all the way to positive 1, right? Because sine value covers everything from negative 1 to 1, so it covers everything. And then it does not repeat itself. Okay, if I go from 0 to pi, it repeats itself. Okay, and it doesn't cover the negative part. So from negative pi over 2 to pi over 2, it covers everything. Okay, so let's go ahead take a look at what happens. So what we will do is we will restrict the domain of the arcsine to negative pi over 2 to pi over 2. So, well, not the domain, actually not the domain, but the range. But let's write it like this. Okay, so let's write it like this. So x equal to, okay, sine of y. Okay, so pay attention, x equal to sine of y. So that means y is, but then we're going to restrict y between negative pi over 2 less than y to positive pi over 2. Okay, to pi over 2. So that means y will be equal to arcsine of x. Okay, and x of course is restricted between negative 1. I'm sorry, the input here, I'm sorry. Alright, this is the input of the function, right? Input of the function, the output of the function. The output of the function will be restricted to negative 1 and 1. Okay, that's the output of the sine function is always between negative 1 and 1. And here, the y I'm using as the input, so it will be restricted to negative pi over 2 less than equal to y less than equal to pi over 2. So this will be the domain for arcsine. Okay, let me go ahead and write it off on the bottom here. Okay, so the domain of arcsine will be between negative 1 and 1, and the range of the arcsine, which is the output of the arcsine, will be restricted from negative pi over 2 to pi over 2. So that means arcsine will only operate between negative pi over 2 to pi over 2. So arcsine will only operate in the fourth quadrant. This is the fourth quadrant, and the first quadrant. Okay, and so what it means is that if x is between 0 and 1, if x is positive greater than 0 and 1, you will have an angle returned to you in quadrant 1. Okay, and if x is negative, if you have an input for arcsine is negative between 0 and negative 1, and then your output angle will be in quadrant 4. So here arcsine, if I input a positive in arcsine, I will return angle in quadrant 1. If I input a negative number into arcsine, I will return the angle in quadrant 4. So let me give you some examples here to demonstrate what's going on here. So let's go ahead and do this. Alright, so let's go ahead and do something very starting with pi over 3. Okay, so sine of pi over 3 is equal to square root 3 over 2. That's sine of 60 degrees. So that means arcsine of square root of 3 over 2 should be equal to pi over 3. That's correct, right? Okay, so that's basically what the concept is. Now, what about sine of negative pi over 6? Okay, negative pi over 6 is down there in fourth quadrant. Sine of negative pi over 6 is equal to negative 1/2. Okay, so that means arcsine of negative 1/2 is equal to pi over 6. Okay, so far so good, no problem. But now let's go ahead and try. What about sine of 2 pi over 3? Now, sine of 2 pi over 3 is in second quadrant. That's correct. Second quadrant is equal to square root of 3 over 2 also. However, if we put in arcsine of square root of 3 over 2, we will only get back the correct the angle in quadrant 1 is pi over 3. It's not 2 pi over 3. We will never get back 2 pi over 3 because the 2 pi over 3 is outside the range, outside this domain and range here. So this is a very important thing, okay? So even though sine pi over 3, sine 2 pi over 3 is square root of 3 over 2, but arcsine square root of 3 over 2 is not going to be equal to 2 pi over 3. The arcsine of when you do arcsine of any angle, the angle we return will only be in quadrant 1 or quadrant 4. You will never return any angle in quadrant 3 and quadrant 4. So that's something you have to pay attention to. Okay, all right. Now, let's go ahead and do this. Now let's take a look at other situations. What about what about sine of arcsine of an angle? Okay, let's say square root of 3 over 2. What would that be equal to? Okay, well, let's take a look at this situation here. So let's evaluate the inside. What's arcsine of square root of 3 over 2? Now, arcsine of a positive number will always return us the angle in quadrant 1. So we're asking ourselves, what is the angle that has a sine value of square root of 3 over 2 in quadrant 1? And if you look at our unit circle, we say, well, it's pi over 3, 60 degrees. But sine pi over 3 is square root of 3 over 2. Okay, so that means this tells us, okay, this demonstrates that sine of arcsine of x will always equal to x. Okay, but would the opposite be also true? Well, let's try that. What about arcsine of sine of, let's say, pi over 3? Would that be equal to pi over 3? Okay, well, let's take a look at this. Arcsine of sine pi over 3. Sine pi over 3 is square root of 3 over 2, but arcsine of square root of 3 over 2 is in first quadrant, is pi over 3. Okay, that's true. But what about this? What about arcsine of sine of, let's do 2 pi over 3, which we used already. Okay, well, 2 pi over 3, sine of 2 pi over 3 is also square root of 3 over 2. However, arcsine of square root of 3 over 2 does not return that, does not return 2 pi over 3. It only returns pi over 3. So this, when you do arcsine of sine of x, it doesn't necessarily give you back to x. So arcsine, this is true for all x, okay, which is the input. Well, the input of x is restricted between 1 and negative 1. But here, if we do arcsine of sine of x, that will only be true if x is between negative pi over 2 and pi over 2. It will not be true if x is not in first quadrant and fourth quadrant. Now, but when we treat fourth quadrant, we are actually dealing with the negative part of the fourth quadrant. It's from 0 to negative pi over 2. So from 0 to negative 90 degrees, rather than from 270 to 360. Even though it's the same angles, but they're coterminal. But then we're dealing with the negative measure here. Okay, so this is a very important rule that we can help us understand sine and cosine, sine arcsine, and arcsine and sine. Now, in regular inverse functions, usually if you have an inverse function f inverse of x, E always equal to x, and f of inverse of x is always equal to x. Now that is true in regular inverse functions, but in sine functions it's not necessarily true. So it depends on the It depends on your input. Really, the domain is something that we have to watch out for. But of course, sine arcsine x is always equal to x. That's going to be true, because x will always be equal between -1 and 1. But if x is outside -1 and 1, then it's undefined, because there's no arcsine of anything above that. Okay, it's not possible. It's not defined. All right. Now, what does the graph of arcsine look like? Okay, so this is the sine graph, and let me just go ahead and show you the graph of arcsine, okay, which is inverse sine of x. So as you can see, it's that little piece, okay, of graph here, and as you can see, it started from -1, -pi/2, but that is exactly the inverse of this point, right? You see how those 2 points are switch around, and then here, pi/2 1, that's the inverse here, 1 pi/2. So this point is pi/2 1, and this point is 1 pi/2. Okay, because it's the exact inverse. As you can see, this piece is reflected across the diagonal line y equal to x. It becomes the orange graph. So that this little piece of function is your arcsine. So arcsine only operates in the fourth quadrant. It only returns you the angle, in fourth quadrant and first quadrant. Okay. All right. So that is our arcsine function, and then let's take a look at arccosine and see if we can go ahead and talk a little bit about arccosine function today. All right. Now, so let x equal to cosine of y, okay? So that means y would be equal to arccosine of x, or inverse cosine, okay? So that means the domain for x, the input for arccosine has to be between -1 and 1. And what would cosine be limited to? Now, cosine would be, the output of cosine would be limited to from 0 to pi. So it's a little bit different, okay? Let's go ahead and let me show you the diagram here. Let me graph cosine very quickly. So this is cosine. Now, as you can see, from 0, cosine goes down to negative, and then it passes through all the unique value of cosine. Cosine travels to all, cosine goes through all the unique values from 0 to pi, as you can see. Now, if we go from -pi/2 to pi/2, it will repeat itself. So, going from 0 to pi, it will not repeat itself. It will go from 1 to -1. So, that is what cosine will be. And let me go ahead and show you the arccosine function just right now, as you can see. Alright, arccosine looks a little bit weird because, the input goes from -1 to 1, as we have talked about. Okay? -1 to 1. This is you see, 1, 0 is the reciprocal of 0, not the reciprocal, the inverse of 0, 1. And this point, pi -1, if you switch up, it will be -1 pi. So arccosine goes from -1 to 1, but its output goes from pi to 0. Okay? Alright, so that's what it says. The input goes from -1 to 1, the output goes from 0 to pi. Okay? 0 to pi. Now, let's do some examples here to show you. So, let's do some cosine. Okay? Let's go do cosine of pi/4. Cosine of pi/4 is square root 2 over 2. Is that right? Square root 2 over 2. You should know this by heart, or if not, you can look at your unit circle. So that means arccosine of square root of 2 over 2, it should be equal to pi/4. Okay. Now, what about cosine of 3pi/4? Cosine of 3pi/4 is negative square root 2 over 2. Okay, so if we do arccosine of negative square root 2 over 2, it should give us 3pi/4. Now, pay attention. Now, when we do arccosine of negative number, okay, the angle returned to us is in quadrant 2, because arccosine goes from 0 to all the way to pi. So if I do arccosine, if I do input was positive, I will return an angle in quadrant 1. But if the input of my arccosine is negative, it will return to us an angle in quadrant 2. Because remember, in quadrant 2, cosine is negative. So arccosine of negative square root 2 over 2 should give us an angle in quadrant 2. So we have not instead of quadrant 4. But arcsine, okay, arcsine operates in quadrant 1 and returns in quadrant 1 and return your angle in quadrant 1 and quadrant 4. So that's this major difference here. Alright, So let's do another one. So let's do arcsine. How about arccosine of 1/2? Well, arccosine 1/2. So we're going to be looking in quadrant 1 because the input is positive. So the angle in quadrant 1 that has a cosine 1/2 should be square root. Should be pi over 3. Excuse me, pi over 3. So it's 1/2. What about arccosine of -1/2? Okay, -1/2 would be 2 pi over 3 because that's what the second quadrant angle that has a cosine value of -1/2. Okay, all right. So if I do cosine of arccosine of x, would I always get back to x? Yes, I will always get back to x as long as x is between what? -1 and 1. Now if I do arccosine of cosine of x, would I always get back to x? Well, only if your x is between 0 and pi. So only if you input an angle between 0 and pi would those be true. Would those statements be true? Okay, so that's something you have to be aware of. Okay, all right. So I think today we ran out of time, and then we only talk about arccosine and arcsine, but that's very important. Hopefully you can understand the concepts a little better. Please leave any comments and questions in the comment section below, and then next lesson we will continue to discuss inverse functions. We'll do some more examples, and we'll also talk about the other inverse functions, inverse tangent and secant, cosecant, and cotangent. All right, thank you.